Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you to everyone joining us from around the world. Please let us know where you are watching from. And also welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. Today, I'm excited to be joined by friend and colleague, Dr. Sgro, who is the Exoplanets Lead over at Unistellar, our partner in community science. And we are here to talk about the community science work that they are doing over there, and in particular, exoplanets. Exoplanets, of course, are planets that orbit stars outside of our solar system. And ever since Kepler and TESS launched, we've been finding thousands of candidates. We went from a handful to almost 6,000 confirmed exoplanets at this point, with a lot of candidates out there as well. And one of the problems that we have, right, Lauren, is that there's not enough telescope time to confirm some of these planets that are out there. So what is this? I'm going to start it off this way. So can we confirm, can we find exoplanets from home now? Is that what this is all about?
So hi everyone, really excited to be here. Great question. We can definitely confirm exoplanets from home now, and that's what all of this is about. So finding exoplanets, finding the very first indications that an exoplanet may be orbiting around a star other than our sun. So that's what an exoplanet is, right? A planet around another star. It's a little bit harder. So a lot of times we will see indications of an exoplanet passing in front of its host star from exoplanet searching space telescopes. So for example, TESS, that's NASA's Transiting Exoplanet Survey satellite, scans the whole sky, focuses on different areas for a particular period of time, and catches these signatures of a exoplanet passing in front of its star. And from when an exoplanet transits or passes in front of that star, you see the star's light dip. So basically a decrease in brightness. And that's how these bigger professional telescopes are seeing indications of exoplanet transits. Now, we from home have an opportunity to follow up on that and basically take what a space telescope, professional telescope is seeing, and then make our own observations and potentially confirm that existence, because just one little dip in a light curve is not quite enough for us to confirm. So that's where community scientists come in.
So when Kepler was up, that was one of the things that it was part of the rules, was to confirm an exoplanet, you had to have it pass 3 times, which was why we found a lot of these like close in larger planets early on, because they were going quickly, they orbit close in, they're very big, so they block more of the light. So if you look at some of those early discoveries, there definitely was a little bit of bias in the results. But now what you're saying is we have these community scientists that we can now work with to make these confirmations happen faster. So explain a little bit about what community science is. I know a lot of us have participated in it in one way or another over the last years. If you followed SETI, I'm sure most of you will like to tell me that you've done SETI at home, which is not ours. I wish it's not ours. That belongs to Berkeley. But what is community science? How does this help?
So community science is really a collaborative effort between everybody who's interested in science. So in fields other than astronomy or astrophysics, it can look quite different. There's a lot of like websites or apps where you can go through data or go through images and contribute to people's projects. In the case of astronomy, like you mentioned, there's not enough professional telescopes, and the sky is like really big. So there's not enough professional telescopes, there's not enough professional astronomers, there's not enough of these resources to be pointing at the sky all of the time, investigating. So that's where community scientists come in to fill in those gaps and make those observations that are just as important as those made by a quote-unquote professional astronomer. And I say quote unquote because I don't often feel like a professional astronomer. The letters after the name, once you're taking this data and contributing to science, don't mean a whole lot to me. But yeah, it's a collaborative effort between the community and people that do this for as a career. So anybody who is interested in science and in the community can participate in various projects. In astronomy, it looks like oftentimes taking data with a user's telescope based off of whatever a particular astronomer or group is needing data on.
Mm-hmm. So this program is the one that you're working on is called Unite. It's the Unistellar Network Investigating TESS Exoplanets. So as you mentioned, TESS is a spacecraft we have up. It's a telescope. It's looking at the sky all the time, and it's finding all of these various candidates. So how does the Unite program work? How do you get data from your users? What are they looking for?
Yeah, that's a great question. So Unite is basically a subset of the Unistellar Exoplanet program, where we're basically observing all sorts of stuff, whatever we can send out to our community as opportunities to observe. But with Unite, this is a NASA-sponsored program where basically we are looking at long duration transits, so exoplanets that take a really long time to transit their star, or particular TESS candidates, like you mentioned. Those are exoplanets that we see a signature for, but they're not quite confirmed yet. We're looking at those particular cases and basically telling anybody who's interested, so whether they have a unistellar telescope or not, hey, this is a great opportunity to observe. We're taking this target, we've done the research, we think that it's going to potentially show us something really interesting. And we post that on our website. We post it to our community science Slack channel. Anybody who has a unistellar telescope can join that Slack channel, and we communicate with them via that. It's a great platform. And once we basically say, hey, here's this really exciting target, will you take data? They take data with their unistellar telescope and then upload it to us. Or if they don't have a unistellar telescope, which I've encountered a few times and that data is still really useful, they basically take their data, do the analysis on it themselves, and do a reduction on their data, and then send it to us, and we can use it to what's the word I'm looking for? Combine, that's the word, combine unistellar and non-unistellar data together to get some really interesting results.
And how many exoplanets has the community confirmed? What are we? One of the things that I talk about in the description of this interview is that you have two that were recently published, one in July and one earlier in the year, and you have a hot Jupiter and you've got this sort of sub-Saturn sized one. But those aren't the only two. But how many? What's the number that we're talking about right now?
Yeah. So far. You're really close. So far, there's three that the Unistellar Network has played a part in confirming. There is a sub-Saturn, which is actually the densest sub-Saturn to be first discovered by TESS et al. And then confirmed by the Unistellar Network. And Daniel Peluso, who was with our team previously, led that study, and I got to be a part of that as well. And then there's two warm Jupiters that we've played a part in confirming. One was led by us, and we actually got to work with another community science organization, NASA's Exoplanet Watch, to essentially gather data from a professional telescope based off of what we saw with TESS, the telescope from NASA that I was mentioning earlier. We saw some signatures of a transit, and then we got a little bit more data to help us figure out when it was going to next pass in front of its star. And then the Unistellar Network and Exoplanet Watch observed those predicted transits, and they caught it. And that was super exciting. And that allowed us to confirm the exoplanet and say this is a real planet orbiting a star over 300 light years away. Another is a warm Jupiter that the Unistellar Network took observations of and didn't quite see what we were hoping to see. We didn't see the transit, but even in science, no result it's still a result. And that data was able to help the team that was leading the study to still know when that exoplanet was not transiting its star and further constrain the parameters on the system.
That's always, yeah, like you said, a no result is still a result, and it may tell you no, it wasn't a planet. There are other things that can cause the light of a star to dim, as gas and dust, people, dust, so much dust.
And other stars in some cases. We just had an experience with that. We thought we may be seeing another potential planet that we were trying to confirm, and with some more data, it turned out to be an eclipsing binary, which those of you who may know a little bit more about exoplanets will know that binaries are cool, but they were not what we were looking for.
No, it's like, oh yay, an eclipsing binary, not a planet, but all right. So what is it? So the call kind of goes out to the community on Slack, on the website, and then you get data from people. Is this data being analyzed in-house by your team? Is that something that you're doing, or is that going back to NASA? How does it work from there?
Yeah, so for the most part, when we lead a study, like I was just mentioning, two of those papers, publications that we were on, which, by the way, whenever we have a publication, all of the citizen or community astronomers that contributed data get to be included on that. But for the most part, when we gather data, we are the ones handling that. And oftentimes we have collaborators that may do things with resources that they have that we don't, and that's really helpful. But for the most part, any data that is sent to us, we are the ones processing that and looking for the transit signatures. And I can actually maybe show you what that would look like if you, let me see, here we go. So I'm just going to show you a really quick example of what that looks like. Oh, let's see. Can I do it? Aha! Fantastic. So this is from the warm Jupiter that the Unistellar network led the confirmation campaign for. You can see that in that very top portion where it says test sector 55, that's the original dip in the host star's light that the TESS satellite saw. Everything below that is data from our observers participating in the UNITE program. And you can see that their data, the black data points, it dips at the expected transit time. So it was with this data that we analyzed in-house that we were able to confirm the nature of this exoplanet and find out that it's a warm Jupiter. And adding to the compendium of knowledge there, warm Jupiters are something that we don't quite 100% understand in exoplanet science. We see a lot of hot Jupiters, like you were talking about before, those really massive stars that are really close to the sun. And we think possibly it's expected that warm Jupiters will eventually become hot Jupiters, but there's a few gaps in the knowledge. We don't know exactly how it's happening all of the time. And I hope that as we discover, or as we confirm more exoplanets, that we're going to be able to add a little piece to that puzzle.
I want to welcome in people, and then I want to get back to talking to you about this project. So welcome into people who are watching from, it's getting global again, New Zealand, Texas, France, Ohio, Georgia, California, Sweden, Illinois, Wisconsin, Missouri, more from Georgia, Australia, good day, and anything else? I thought I saw Washington State. So yeah, okay. So watching from around the globe, it seems that's fantastic.
It's amazing.
Thank you everybody for joining in. If you have questions for Lauren about exoplanets or citizen science, please feel free to ask us in the comments. I'm keeping track of them, so let me know. Let us know if you have anything you want to know about. So Lauren, what kinds of so you're right now, the success has been on the larger side of the planets. What kind of stars are we talking about here?
Yeah, so for all three of these planets that I was just talking about that we helped confirm, they're all sun-like stars. Okay. Sometimes we will get stars that are a little bit cooler with candidates that we're trying to go after, but these 3 cases are sun-like stars.
And can the telescopes from Unistellar, can they get down to seeing the red dwarf size stars, because we know that those make up so many of the stars in our solar system? So can we get down and see dips in light for those?
We can. It has been done. We haven't had a kind of featured campaign that we've gone after one of those planets around a red dwarf in a little bit, but we have done it before. It just depends on the system configuration, basically, how big the planet is, how nearby, etc.
What kind of dip in light can the unistellar telescopes, what sort of percentage can they get down to?
Yeah, so for example, I'm trying to pull numbers out of my brain. They're in there. I know it. A typical transit they were looking at may be 1 to 2% of the host star's light.
Okay, so pretty small, all things considered. So that's not too bad.
And we're still looking, though, at massive planets for the most part.
Right.
So still gas giants, even with that.
Right. All right. So we're still not looking. What you're saying is, so far, not talking about Earth or super Earth sized planets here.
Right. No rocky planets.
Those larger gas and ice giants. Okay. How can people get involved? You mentioned earlier that sometimes that you do get data from people who don't have a unistellar telescope. So obviously the easiest way is to have a unistellar telescope, but that's not necessarily in reach for everyone. So how does just an astronomer with a regular telescope of their own, how do they get involved? How does anybody get involved, just in general?
Yeah. So you can go to science.unistellar.com, and that basically gives an overview of our entire citizen science program here at Unistellar and SETI through all of the different science campaigns. And you will find our Unite webpage there on the exoplanet section. And you can also go to NASA's citizen science webpage and see the Unite program there. It will take you to that page, and that has all the information that you would need to know. Anybody with a telescope that is actively taking and recording data can send that. We would just ask that you do a couple of things for us to reduce your data in such a way that we can work with it, just because the science is a little bit easier when you're working with similar instruments. So for example, the unistellar telescopes, they're easy for us to take data and combine all of that together. That's what helps us tackle those really long duration transits. For example, one of the publications I was talking about, there's like 20 hours nearly of continuous exoplanet data from Unistellar. And it's pretty incredible. The way that we're able to do that is because they're all similar instruments and we know how they work. So anybody with a telescope who's recording can absolutely contribute data. We would just ask that you reach out to us first and we can help you through the process.
Okay. So there you have it. And I've, for several of our platforms, I have shared the link to the Unite webpage. And so if there is something that if you want to take a look at our YouTube links in the description, we also have a link to Unite there, as well as the papers detailing some of these discoveries. So I'm gonna look at some of these audience questions here.
Yeah, that would be great.
Let's see. Okay, so Zapfan did ask, and I think we've kind of covered it, but a unistellar telescope can detect a 1% drop in brightness due to a transit. So just to confirm, yes, that is correct. Okay.
So it usually, when we get to that point of 1%, it usually requires more than one person or one person with a really, really clear night.
Okay.
We haven't detected anything with a single person observing below about 0.6%, something in that range. I don't have the numbers in front of me, but yes, it is absolutely possible. People do it all the time if they have really, really good conditions or if we're combining two people's data.
Okay, fantastic. Let's see. Oh, this is okay. More general exoplanet questions coming in a little bit here. So based on what we know from today, this is from TA in New Hampshire. How common are exoplanets? You know, how common do they seem to be? Are we talking every star, every 10th star, every 100th star?
They're more common than not. I don't actually know the statistics off the top of my head. That's actually a side effect of being a scientist. I could tell you all about the particular observations and exactly how a warm Jupiter forms, but can I tell you the exact number of how common they are? No, I cannot, not off the top of my head, but that's a really interesting question. And I know that there's a lot of resources. And it's also going to depend on what star you're talking about, what type of star. So for example, sun-like stars have a much higher rate of having planets than much, much hotter stars. There's a reason for that, and the way that those hot stars kind of eliminate everything else that is around them when they form and doesn't leave much left for planet formation. But sun-like stars and cooler stars often form planets. The particular rate off the top of my head, I don't actually know.
I think I've read somewhere that it's like every other star. So it's like it's not every star, but it's like 50% of stars have at least one planet, and you know, beyond that, they have more than one planet. So we're actually, as we've gotten more and more data, it seems to be that multi-planet systems are as common as single planet systems,
if not more common. That is definitely true. And there's even rogue planets that aren't orbiting any star. It gets crazy out there, y'all.
Yeah, rogue planets, that's a whole other thing.
It is a whole other thing. Sorry I brought that up.
No, it's a fun thing to talk about. Okay, so let's see. This is another. Okay, Cristiano is asking, what do you see as the next big breakthrough in characterizing exoplanet atmospheres? So that's sort of the like, where do you go from here? Yes, we have 6,000 confirmed exoplanets, and you're adding a few more to the kitty. But why? First off, why are we doing this? And what does this lead to? What we're characterizing these atmospheres. So where do you see this all going?
Well, as a SETI Institute employee, I hope that one day we find an exoplanet that could support life as we know it, or maybe a different kind of life. But this is a really, really important question. The exoplanets that we've talked about today, these warm Jupiters that may become hot Jupiters, the ones particularly mentioned today, we could actually observe with JWST and may potentially apply for time for, just because of the way that they orbit their star and pass in front of and behind them, which is really, really great. So for me, the next big breakthrough would be to get that time. Hopefully, I think that in the future, we basically are able to see smaller planets. And detect some potentially, hopefully, maybe one day, things that may indicate signs of life. But as far as these particular planets, warm Jupiters themselves, we don't have a lot of atmospheric data on them. So like I was mentioning, this difference between hot Jupiters and warm Jupiters. Hot Jupiters, we see them really often. They're really, really close to their star. They're pretty massive, more than a quarter of the mass of Jupiter. And they're easy to detect. And we have some good atmospheric data on those. But as far as warm Jupiters, which are a little farther out, we don't have a lot of atmosphere data on those. We think that those may migrate inward to become hot Jupiters. So I would personally be really interested in getting more atmospheric characterization data on warm Jupiters.
Makes sense.
And smaller planets.
And smaller planets. More small planets, please. That kind of brings in a good question. It looks like we have some questions on some of the basics on exoplanets, which that's fine. Everybody, you should ask the questions. So this one is asking, how do you classify an exoplanet? And I think that's a very fair question, because we do say like, oh, it's a warm Jupiter, it's a sub Neptune, it's a sub-Saturn, it's a rocky world. So how does our characterization of these exoplanets work? How do we say it's this kind of planet? What's our determinations here?
Yeah, I really, really love this question, actually. You're going to have to stop me from talking for too long. So like I said, an exoplanet is any planet that is orbiting a star other than our sun. And there's a couple of different ways to get data on those. So for example, the transits, like I was talking about, that is one way, especially to determine the size of a planet. We also look at radial velocity data, and that, I'm going to show you a graph that will see how well it goes over. Let's see. Yeah, so this is radial velocity data. It doesn't look very fun, but I promise that it is. With radial velocities, we basically measure, so say you have your host star, that host star is going to wiggle back and forth along our line of sight, according to the configuration of the system, if it's in such a way that that its orbit, that the host star is moving away or towards us. And we can actually measure that wiggle back and forth, and that's going to be due to some sort of companion, whether it's a star or a planet. And with radial velocity data, we can take this off right now. It's kind of scaring me, actually. With radial velocity data, we can get a mass estimate for the planet as well. So depending on how massive the companion to the host star is, whether that's a star or planet, that's going to affect how much the host star wiggles back and forth, basically how much it moves. So radial velocity data gives us mass estimates. And from a mass estimate and a size estimate together, we can kind of tell in what range a planet is going to be, whether it's Jupiter-sized or Saturn-sized. And often we're using our own solar system planets to classify these. When we say a Jupiter-like exoplanet, it's just because it's like Jupiter. It's around the same size as Jupiter, or around the same mass. But those two particular pieces of information can really help us figure out how large a planet is and how massive. And that's going to tell us which solar system planet it's most like, and perhaps even its density, and tell us, we'll be able to gather from that probably whether it's a gas giant or a rocky planet and what it most compares to.
So this comes down to, when we started the process of looking for exoplanets, we had one example of a solar system.
Yeah, ours.
And it's very difficult to classify things when you have one. So we basically are like, well, we have one big, huge gas giant. We have a second, somewhat smaller gas giant. We've got a pair of ice giants. We have some inner rocky worlds and a lot of little things scattered throughout. And so that's what we have to, like, that's our reference point. So that's what we compare back to. So when you see these things, we're just pretty much comparing to the planets in our own solar system, because that's what we know.
And we also see that most planetary systems out there do not look like ours. Yeah. Which is really, really interesting, which is why studying things like hot and warm Jupiters, when we're not really seeing nearly as many cold Jupiters out there, which is what we kind of call our own gas giants. It's just really interesting, because not every planetary system looks like ours. And the hope is that by figuring out where these hot Jupiters come from and how warm Jupiters may turn into them and what other rocky worlds are out there, by studying other planetary systems, hopefully we'll figure out how our own formed.
Mm-hmm. Okay, one last question from our viewers. Same person wants us to explain the Goldilocks zone, and I think that's very fair. We don't like the term Goldilocks zone anymore. We use more like habitable zone, but can you explain what the definition was and what it's sort of become?
Sure. So the Goldilocks zone is basically this area around a star where an orbiting planet may be able to sustain liquid water. And we know that, at least for us, liquid water is necessary for life. And of course, the Goldilocks zone is going to change. Like its location, that is going to change based on what type of star the planet is orbiting. So the Goldilocks zone is going to be in a different location for every different star, or every different type of star at least. So for example, a really, really hot star, the Goldilocks zone may be really far away, but for a cooler star, like a red dwarf or a sun-like star, that's going to be closer in. Why it was called the Goldilocks zone originally was because it was just right for liquid water.
If you know the Goldilocks fairy tale, and for viewers who are not necessarily familiar with that from Western culture, it's the story of a girl who basically breaks into. There's a lot of breaking and entering in fairy tales. She breaks into
a lot of criminal activity.
Yeah, she breaks into the home of some bears, a mama, a papa, and a baby, and Papa's stuff is always too much, Mama's stuff is too much, and Baby Bear's stuff is just right. So she eats all of his porridge, she sits in his chair, she's found sleeping in his bed, because that's the Goldilocks zone. Would be, it's just right for what
for liquid water.
For liquid water, which is our baseline for habitability. There are a lot of other considerations, but when you're starting to get a lot of planets to make further observations of, you want to kind of narrow in on what ones seem like they have a better shot at again, telescope time, very limited.
Yeah.
It's a very limited resource. So, you know, we do what we can to kind of narrow the prospects. All right, that's pretty much it for the audience questions. So I kind of want to wrap this up, but do you have, are there any observations coming up? Is there anything on the table for Unite, or even any of the other aspects of your community science projects?
Yeah, so right now we have, like I mentioned, just discovered an eclipsing binary instead of an exoplanet, which is quite common. For those of you who don't know, a eclipsing binary is basically two stars orbiting around one another, and that can again cause the light that we're seeing from them to dip periodically as one passes in front of the other. And oftentimes this can look like a transit of an exoplanet. So they get confused oftentimes, and the scientific community has to weed them out in order to find the exoplanets. So if you go to the Unite's website right now, you will see the call for observations for that. But literally right after this, I have another call for observations that I'm going to put out for another potential transit, a candidate that we're basically working with another group at SETI to identify TESS candidates that basically were skipped over by TESS, didn't really necessarily classify them as transit and exoplanet candidates. And we're working with another group who's found some of those that may be really interesting to follow up. And we're calling that particular program Uptempo. Yeah, you'll be able to see that if you go to the Unite webpage. You'll see the description of the Uptempo project, where we're trying to track down these kind of exoplanets that got skipped over. So right after this, I will be announcing a new one. So watch out. It's going to be mainly a southern hemisphere observation. So my friends in Australia and New Zealand specifically, I will be looking to you and really excited to see if we can catch this.
Fantastic. Well, I look forward to finding out the results from that. I want to just quickly shout out to some people watching from Ohio, Cambodia, and more in California and Argentina. Hello. So we do have some Southern Hemisphere viewers. So if you have a unistellar telescope, and even if you don't, there are some things that you can take a look at for community science purposes. So
yeah,
Laura,
and sorry,
go ahead.
No, I was just going to say that everybody who participates in these, if we get a publication out of them and we get to make some discovery, you get included on those publications and you get to really contribute to meaningful science. It's meaningful, of course, whenever we do science, but some of these end up being groundbreaking discoveries. For instance, the most recently published exoplanet paper that Unistellar was a part of, that another group at NORA Lab and Penn State led that we contributed to, but we missed the transit. That ended up being the most eccentric transiting exoplanet ever to be discovered. And it's actually, I know I'm like holding you up, but I'm going to show you a picture of it. This is from a press release. It's really cool. And I did not make this. This is from the press release from the group who actually led this, even though we're part of the paper. But this is such a cool thing to be a part of. It's a groundbreaking stuff, and it's so meaningful, I think, for this to be accessible to anyone and everyone that can make an observation. So please come join us. Please check out the Unite website. And I just really look forward to seeing everybody's observations. This has ended up being a really great program. And the more people that we have, the more discoveries and confirmations we can make, and the more science we can do together.
That sells it right there, Lauren. That was fantastic. Thank you, everybody, for joining us. Thank you, Lauren, for talking to us today. Congratulations to your community scientists and observers.
They're amazing.
And congratulations to the community scientists who have made these observations and now have your name immortalized on a peer-reviewed scientific paper, which, of course, as scientists is that high standard we all hold. So Lauren, I expect you to be back frequently. Lauren also does a lot of stuff coming out of Unistellar, and they'll be having a citizen science, community science Q&A next week.
Yes.
Yes. And then there's something about a comet. Can you kind of drop a little bit about the comet? Because I know while you're the Exoplanet Lead, everybody talks to everybody over there. So what's the deal with the comet?
Yeah, we're a very small team. The comet, you will be seeing more about that very soon. But Comet A3, C2023 A3, is going to be approaching, it's the closest point it'll get to the sun on September 27th, and then its close approach to Earth on October 12th. And this comet has been slated as potentially the comet of the decade. It could be brighter than anything else in the night sky aside from the moon. It has the potential to get that. So we're really sending the network after that to do some science on it and track its brightness, because nobody really knows how bright it'll get, but also just to get some really amazing images of this opportunity. It's newly discovered too, so we don't know what it's going to do. It's unpredictable but exciting, and we haven't seen this before. So stay tuned.
Yeah, definitely stay tuned. And next week I will be talking to the comet lead, Ariel Grakowski, and we will be discussing this comet and what probably a bit more about what a particular contest might entail. So we shall see. Everybody do stay tuned. Thank you for joining us today. Of course, this has been SETI Live. Thank you, Lauren, for being here. Thank you, everyone, for watching from around the world. And once again, SETI Institute is a 501c3 nonprofit. We are funded by donations. And to keep programs like this running, if you go to SETI.org/give-now, or just go to SETI.org and find the bright red button to donate, you can help contribute to community science, to outreach and education, and keep all these programs running. So thank you, everybody, for watching, for joining us today. Make sure you hit those like and subscribe and share buttons, and we will see you next week to talk more community science. So thanks, everyone.